Hello, welcome to the course. My name's Blake Jackson, and I'm going to be annotating all of the written notes that are on Husky CT for you. These are notes from a fall semester course, so the weeks that the files say don't necessarily correspond to the weeks in a summer course, but all the material is the same, and it's broken up in a way that a certain number of weeks correspond to test 1. I think weeks 1 to 4 correspond to test 1. So it's still usable. And rather than rewrite all of the notes just for summer course, I figured I would just go through them and annotate the notes. So first section, 1.1, definitions and terminology. What is a differential equation, right? A differential equation is, by definition, an equation which involves a function and its derivatives, right? So it's an equation involving the derivatives of one or more unknown functions. We call these the dependent variables, and normally we denote them by y. With respect to, I use a lot of abbreviations, so I'll try to explain what they are. With respect to one or more independent variables, and usually these are denoted by x or t. So here's an example of a differential equation down here. Dy dx equals 3y, right? So in this case, y is our dependent variable, and x is our independent variable. And one of the solutions to this equation is this function here. So an important thing to note about differential equations is that solutions to the differential equation are functions, right? In algebra 1, right, solutions to an equation are like numbers. But here, solutions to differential equations are functions y, right? Very important distinction. I'll try to be very clear about that as we go on. How do we know that this is a solution, right? How do we know that this function y is a solution to this differential equation? Well, it's pretty easy. We can just plug it in, right? We can just plug it in and check. So we know what y is equal to. Y equals e to the 3x. And that means we can find its derivative, right? And the derivative of y is, with respect to x, is dy dx, right? The derivative of y with respect to x is dy dx. And the derivative of e to the 3x with respect to x is 3e to the 3x, right? So by differentiating both sides of this equation, we obtain this equation. And then we're just going to plug in y and dy dx into this differential equation, right? And if we plug dy dx in to the left-hand side and we plug y in to the right-hand side, you'll see that 3e to the 3x is equal to 3e to the 3x, which means that y equals e to the 3x is a solution to this differential equation. And in fact, this is the only solution to this differential equation. So notation, so since there's a lot of people throughout history who have done this calculus and there's an extreme variation in notation, we're going to try to fix our preferred and our not so preferred notations. So my favorite notation, because there's no mistaking who the dependent and independent variables are, is the Leibniz notation, right? This is my number one, right? I like the Leibniz notation. It will get clunky later, so the prime notation is also okay. So in this case, in the Leibniz notation, we denote the first derivative of y with respect to x as dy dx. And then the second derivative of y with respect to x is denoted by d squared y dx squared, and so on until you get to the nth derivative, right? In general, the nth derivative of y with respect to x is dny dx to the n. If it's understood that y is a function of x, it's sometimes a little easier to use the prime notation, right? And for prime notation, the first derivative of y is denoted as y prime, the second derivative is y double prime, the third is y triple prime, and then after that we do this little parenthesis business, right? So you write y to the nth, right? That's the nth derivative of y. And in physics, sometimes you'll see the dot notation, and for physicists, or engineers, you really don't need higher than a third derivative in most cases. So the dot notation really only is good up to the third derivative, and that's as far as they usually use it. But we're going to stick to these up here, right? We're going to stick to these two. Partial derivatives, for Leibniz notation, you do like the partial symbol. So for regular derivatives with a Leibniz notation, right, it's a d. It's a lowercase d. But for the partial derivatives, right, it's a little partial symbol. And this can be useful if, in this case, say u was a function of x and t, right, together, right? If u is a function of both x and t, then you can take partial derivatives of u with respect to x or with respect to t, or a mixture, right? And those are denoted like this in the Leibniz notation. But this gets really clunky, right? You can imagine how long and ugly some of these derivatives might look, right? So I prefer the subscript notation. So again here, I'm assuming that u is a function of x and t, right? And in this case, you can denote the derivatives with a little subscript, right? So this would be the partial derivative of u with respect to x, the partial derivative of u with respect to t, and then the mixed partials. There are some famous differential equations. A lot of these are partial differential equations because, as it turns out in life, right, in the real world, quote unquote, most things are functions of multiple variables, right? And especially like when you're talking physics, right? Things are functions of 3 spatial dimensions, right? Left, right, forward, back, up, down, and a time dimension, right? And so here's the 3D heat equation, right? And so basically what this says is the partial derivative of some heat function u with respect to time should be equal to the second partials of u with respect to each of the spatial dimensions summed up together. And the idea is any u which satisfies this differential equation, right? Any function u that satisfies this differential equation is a heat equation, by definition. We also have Laplace equations, right? Or I guess we call this the 3D Laplace equation. This is a differential equation again, right? It's a function, it's an equation involving an unknown function u and its derivatives. And any u satisfying this is said to be a solution to the Laplace equation. There's others that are more complicated that involve what's called initial conditions, right? So, I mean, you can just ignore this differential equation. It's pretty, it's fairly ugly, and I'm not really going to go into what all the things mean, but the point is that, you're taking some derivatives of some functions with respect to variables, right, inside of an equation, which makes it a differential equation. We're going to see in later sections that stipulations that follow a such that are called initial conditions, right, or boundary conditions sometimes. And so in this case, we have initial conditions on phi, which is our unknown function here, which says that phi at the point 0 should be 1, and the derivative at 0 should be 0. And here, phi measures the density of at radial distance eta from the center of a white dwarf star. Here's some easier ones that you've probably seen in like first year physics, the kinematic equations. This says that velocity is the derivative of position with respect to time, and that acceleration is the derivative of velocity with respect to time, which is the second derivative of position with respect to time. Here's an even more complicated one. This is describing the gravitational force on a person inside of an in-body space, right? So let's say we have in-point masses labeled m sub I sitting in 3D space with position vectors qi for each of them, right? And if you want to know the the equation that governs the position and acceleration and velocity of these objects is this, right? This says that the mass times the acceleration of a specific body I should be the sum of all the forces acting on it, right? So this is another differential equation. And again, we don't need to memorize these differential equations. I'm just showing you that they are pretty ubiquitous in physics and biology and chemistry and a lot of the natural sciences. And the last one, or I guess second to last one, is the Navier-Stokes equation. So this says whatever this equation means, right? But it involves an unknown function u and its derivatives, right? And if you can prove that so-called smooth solutions to this equation exist, you can win $1 million, basically. And if you want to read more about this equation, you can see the paper, Real-Time Fluid Dynamics for Games. And last but not least, let's talk about Schrodinger's equation. This is a pretty famous equation, right? It has a lot of stuff going on in it. It's got the imaginary unit, I. It's got Planck's constant. It's got this unknown function, psi, of x and t. It's got the mass of a particle. It's got a potential function, and it's got this wave function, right? And for any particle, right, its wave function has to satisfy this differential equation, right? Schrodinger's equation for one particle in a single dimension. Okay, so these are a bunch of examples of differential equations, and like I said, we're not going to get to any of these because they're all partial differential equations, right? Most of these are all partial differential, except for this one. But these involve partial derivatives. And since this is an elementary differential equations course, we're not really going to focus on the partial derivative differential equations. So let's talk about how we can classify differential equations. There's three main classification branches, I'll call them, right? The first is classifying a differential equation by its type. You can have an ordinary differential equation or a partial differential equation. And it's pretty easy to tell what the difference between these is, right? An ordinary DE only involves ordinary derivatives, and a partial DE involves some partial derivatives, right? And obviously in this course we're focused on this branch, right? This branch. The next way you can classify a differential equation is by what's called its linearity. This one takes a little of explaining, but basically the delineation is into linear differential equations or nonlinear differential equations. And again, this course is mostly going to focus on these up here. We will see some nonlinear differential equations, and I'll try to point them out when I can, but for the most part, we're going to focus on the linear flavor. And last but not least, you can talk about the order of the differential equation. And this one's really easy to describe because it's just the highest derivative that exists, right? So if we think about, if the highest derivative in the whole equation is a first derivative, then that's a first order differential equation. If the highest order derivative is a second order derivative, then that's a second order differential equation, right? And you can go up as high as you like here. This one is an endless list, right? It goes on forever. But, just to reiterate, this course is going to focus on ordinary, linear, first and second order differential equations. So here's the type, right? Ordinary differential equations, all functions involved have a single independent variable. Very easy to identify, right? If you see any partials, right? This is not an ODE, right? If you see any partials. If you see any partial derivatives in the whole equation, right? Any partial symbols, it's a partial differential equation. Otherwise, it's a ordinary differential equation. The next one is the order, right? So the order of a differential equation is just the order of its highest derivative, right? So here's some examples for you. The order of this differential equation, right, the order of this derivative is 2, right? This guy right here has order 2. And why is that? It's because it has 2 derivatives, right? 2 derivatives. What about number 2, right? The order of this is 1, right? The order of this is 1 because it only has a single derivative. Now, that single derivative is being squared, but this is still a first order derivative, right? So second derivative, first order derivative squared. This one's pretty easy. It's a fourth order, right? This one, again, same as number 2. This is a second order derivative. Even though it's to the 6th power, it's just a second order derivative. And last but not least, I don't know why there's a 6 here. Ignore that. But last but not least, this guy right here, right? 3 derivatives, third order. Third order. Let's do some examples of this. Right, let's look at some examples and decide if these differential equations are ordinary or partial and what's their order. Looking at this equation here, right, we see that the only derivatives involved are ordinary derivatives, right? There are no partial symbols anywhere in here. So we can safely say this is an ODE. And the order, right, is the order of the highest derivative in the whole equation. So if we look from right to left, right, this term has no derivatives. This term has no derivatives. And this term has a single derivative, right? So this is a 0, this is a 0, and this is a 1, which makes this a first order equation since the highest derivative is 1. Okay, second equation. Immediately, this tips me off, right? This is a PDE. The order of this PDE, well, I see this is the second derivative here, right? There's a second derivative here, and there's a 0 derivative here. So the highest of these numbers is 2, right? And since the highest order of any derivative in this equation is 2, this is a second order equation. Third equation, I'm not seeing any partial symbols, so it's an ODE. And this is a first order derivative, this is a first order derivative, this is a 0, this is a 0. And the highest derivative order in this equation is 1, so it's a first order equation. Last but not least, number 4. This subscript notation is used in a partial derivative sense, so this is a PDE. And to find the order of this guy, this is a second order derivative, and this is a 0th order derivative, which makes this a second order PDE. Okay. Sometimes, instead of seeing a ODE written in the Leibniz notation or in the prime notation, we will see it in the differential form version. And this is pretty simple, right? It's just writing this like some function of x and y dx plus some function of x and y dy equals something over here possibly, right? And if you treat dx and dy like something you can divide by, then you can rearrange this a little bit just by dividing by dx. And you can get back to this, right? I guess this has to be 0 over here. If you divide both sides by dx, right, then you can see that we get to this second equation down here. And in this case, this looks more like a first order differential equation, right? So sometimes we're going to see a lot of examples of things written in this form. So for example, we can take the first equation from before and we can rewrite it into the differential form, right? Just by rearranging. So we multiply through by dx everywhere, right? Multiply through by dx, that cancels out the denominator on this guy. And then we're going to group up the dx terms together on the same side of the equal sign, and then you're in the differential form. Okay, the hard one to describe out of all the classification schemes is linearity, right? the short way to say it is that y and its derivatives have to be not multiplied together, right? So y and its derivatives have to be to the first power and cannot be multiplied together, right? The fancy way of saying it is that a differential equation is linear if you can write it as coefficient times some derivative of y, right, to the first power, plus some function of x times the n minus first derivative of y to the first power, right? Go on, go on, go on forever. Plus some coefficient, a function of x, right, times y prime, again, to the first power, plus some function of x times y equals f of x, right? Where these are all differentiable arbitrary functions that do not need to be linear specifically. Sometimes it's much easier to learn by doing, so let's just go through some examples of differential equations and say if they're linear or not, right? When you're given an equation in the differential form, it can be hard to tell if it's linear or not, right? What we care about is y and its derivatives, right? It's y and its derivatives. So what we need to do first is to put it into the normal form. So we're going to divide through by dx everywhere, right? Divide through by dx on both of these, and I guess as well over here, right? The dx goes away, and we're left with 4x dy dx, right? And then we have this x minus, or y minus x term we can move across to the other side if we want to. Doesn't really matter. And then we get to this, right? Now remember, in order to be linear, we only care about y and its derivatives, right? Y and its derivatives. In this case, we see dy dx, right, is by itself to the first power, right? There's no other y's out front, only x stuff. So since this dy dx is to the first power, this first term is a linear term, right? And then we go to the next term, x, just x by itself, no y's, linear as well, right? And then you look at the last bit. This is a y. It's to the first power, and it's not multiplied by any other derivatives of y, right? That makes this whole equation linear, because each term is a linear term, right? Each term is a linear term. Here's an example of a nonlinearity, right? If you look at this term here, right, we can see that y and its derivative will be multiplied together. That's not allowed. That's nonlinear, right? This right here is a nonlinearity. If you were to FOIL this out, right, you would get y prime minus y prime, right? This second part here gives you a nonlinearity, right? Y times its derivative is nonlinear. Let's look at the next one. This bit here is fine, right? This is a second derivative, right? This is a second derivative. But it's to the first power, right? It's all raised to the first power. So this is actually a linear term, right? This is a linear term on its own. That's okay. What's nonlinear is a function of y, right? Since y is my dependent variable, having y inside of a sine function, that's nonlinear for sure, right? Nonlinear. Here's another example. This one looks more complicated than any of the others we've seen, but it's still a linear differential equation. And why is that? This is a function involving only x's, right? This bit is a third derivative of y, but it's to the first power, and it's not multiplied by any other y's, so this bit here is linear. Then we move on to the next term, a function of x. Okay, that's fine. A second derivative of y. This is also not multiplied by any other y's, and it's to the first power, so this is also a linear term. right? Y by itself, linear, easy. Just x's, no y's to be found. This bit here is also linear, right? That means this whole equation, since each of the terms is linear, right? Each of these terms is linear. The whole thing is linear. So this is the last, I guess not the last, but this is the second way that we okay. The last of the three ways that we haven't talked about yet. Ways to classify a differential equation. Excuse me. Let's talk about solutions to a differential equation, right? Let's have some function of x, y, and its derivatives, right, on the left-hand side equals 0. This is what we call a differential equation in general form, right? I don't know anything about this other than it's an ordinary differential equation. All right, so technically this is like an ODE in general form. So everything that has anything is on the left-hand side, and then on the right-hand side is just 0. This is what we call an ODE in general form. Then any function phi defined on some interval I and having at least n derivatives that are continuous on some interval I is said to be a solution if, when you plug in phi and its derivatives, it satisfies this equation at the top here for all of the x's in an interval. Again, this is a little hard to see, but if we think back about the very first thing I showed you up here, right? You don't have to change symbols, right? I just said, here's a differential equation, right? And here's a function phi that when you plug it in for y solves this equation, right? That's what a solution is. And it solves it on the whole interval in that case. So as we saw in the first example, it's down here. Y equals e to the 3x is a solution of this on the whole real line, right? And I just moved this 3y across from the other side. That's all that happened here. So this function here is like my phi, right? This is like phi of x. And if I find its derivatives, its first derivative technically, and I plug that in here and I plug that in here, it solves this equation for any x, right? For any x, which makes it a solution. Now, we're going to get kind of messy with this eventually, but the point is that solutions and intervals are supposed to go hand in hand, right? Whenever you have a solution, you have to say where it's defined, right? Every time you give a solution, you say where that solution is defined. So solutions in these intervals of solution go hand in hand, basically. You can't have one without the other. So let's look at this example. We want to verify that y equals x e to the x. So again, this is my phi of x, right? I want to verify that this is a solution to this differential equation on this interval. So what am I going to do? Well, I'm going to take this function right here, phi, and I'm going to find its derivatives. I need to find phi prime of x, and I need to find phi double prime of x, right? And why do I need to find those? Because this is an equation which involves two derivatives, right? So I need to find, this is phi, right? It's going to go in the place of y, and then I need phi prime, and I need phi double prime, and that's going to go in the place of y prime and y double prime. So in order to check this is a solution, I take my solution, my candidate solution, and I find its first derivative, right? And if you've forgotten the product rule, right, this is a good time to go back and refresh yourself on the product rule and the quotient rule and the chain rule, because we're going to be using them a lot. So anyway, the derivative of this, right, this is a product of functions of x, right? A product of functions of x. When you take a derivative of a product, you get derivative of the first, keep the second, that's here. And then you get derivative of the second, keep the first, constants here. So the first derivative of this solution is y prime equals e to the x plus x e to the x. And then if I take a second derivative, I'm taking a derivative of this function, derivative of e to the x is e to the x, and derivative of x e to the x is this, right? Same thing we got the first time. And if I collect up terms, I get 2 e to the x plus x e to the x. And then all I need to do is to take these and plug them in, right? Plug them in to the differential equation. And if I can plug each of these things into the differential equation and it gives me 0 on both sides, then this is a solution on all the real line. So what do? Just what I said. I take y double prime and I plug in for it, right? I take minus 2y prime, and instead of y prime, I take minus 2 at e to the x plus x e to the x. And then plus y becomes plus x e to the x. And if you check over here, I've got a plus 2e to the x. I've got a minus 2e to the x. These terms will cancel. All right, this term and this term cancel. I've got a I've got an x e to the x. I've got an x e to the x, and I've got a minus 2x e to the x. Those three terms will cancel. So I've got this term canceling with this term, and I've got these three terms canceling, and that gives me 0. Which means when I plug in this solution, x e to the x, into this differential equation, I do get that it's equal to 0, right? Which means this function is a solution to this differential equation on this interval. There's also a trivial solution, right? The trivial solution. If I take y equals 0 and I plug it in here, I find its derivatives and I plug it in, you can see that y double prime will be 0, y prime will be 0, and y will be 0. And 0 plus 0 plus 0 is 0, right? This is called the trivial solution. Y equals 0 is always a solution to a differential equation that has no constants equals 0. Right, we call this a homogeneous equation. There's a related notion called implicit solutions. Now, if you remember, I guess it would be Cal 1, right? You might remember taking implicit derivatives, right? Taking implicit derivatives using the chain rule. Well, this is kind of the same idea, right? Sometimes we can write explicit solutions. That means we can write a solution as y equals some function of x, right? But it's not guaranteed that our solution will have this form. Sometimes the y's and the x's will be mixed up and we can't separate them out, right? Sometimes we can't separate y and the x's out into this form. And in that case, we have what's called an implicit solution. Here's an example. Here is an equation of a circle with radius 5, center of the origin, right? I want to show that this relation here is an implicit solution to this differential equation, right? And in order to do that, you have to take what's called an implicit derivative. So if you don't remember how to do that, go look up implicit differentiation, right? We're going to treat, in this relation, we're going to treat y like it's a function of x, even though it's not written like that, right? We're going to assume that y is a function of x. And we're going to take a derivative of this whole equation, dx, right? We're going to take a derivative dx. Here's how you do that, right? You take the equation and you take d dx of both sides. Derivative with respect to x of both sides. The derivative of x squared with respect to x is 2x. That one's pretty easy, right? The derivative of y squared with respect to x is a little harder because we're treating y like it's a function of x, right? So this part here is really like the derivative with respect to x of y, a function of x, right, all squared. And in that case, we have to use what's called the chain rule, right? The chain rule. The chain rule says you take the derivative of the outside and you keep the inside, right? Derivative of the outside, keep the inside is 2y. And then you multiply by the derivative of the inside. And here the inside function is y. And the derivative of y with respect to x is dy dx. And on the right-hand side, or the left-hand side, this is the right-hand side. On the right-hand side, when you take a derivative of 25, you get 0, right? And then we're going to rearrange this, right, to solve for dy dx. So that means moving this term across the equal sign, right, gives you this. We get 2y dy dx equals negative 2x. And dividing both sides by 2y, right, cancel the 2's, we get dy dx equals negative x over y. And if we look up, right, we said that this was an implicit solution to this differential equation. And in fact, that is true, right? That is true. Because if you implicitly differentiate this, you can rearrange it to look like this, right? That's what we just did. We implicitly differentiated and then we rearranged it to look just like that differential equation. Just like that differential equation. Making this an implicit solution. Making this relation an implicit solution to this differential equation. So again, if you've forgotten how, please take the time to go reread implicit differentiation or watch a Khan Academy video on it or something, because it's going to come up again. Okay, next up we got families of solutions. A lot of times we'll have solutions up to constants, right? You can multiply out front by a constant and you still get a solution, right? And that's okay. That's okay. That happens a lot, right? Ooh, excuse me. So here's an example of a family of solutions, right? So for any choice of c, this family, y equals cx minus x cosine x, is an explicit solution to this linear first order equation, right? This linear first order equation. How can we check? Well, I've got an equation here, an explicit solution. All I need to do is find its first derivative, and then I can plug in y and plug in its first derivative, and I can check both sides. And if both sides of the equal sign are equal, then that means that this is a solution, right? So I take my y, and I take a derivative dx, right? Taking a derivative dx. The derivative of c times x is just c, and the derivative of x cosine x, that's going to need a product rule, right? So you take the derivative of the first, keep the second, that gives you a cosine. Take the derivative of the second, keep the first, that gives you an x and a negative sine x, right? And then distributing this minus sign that was out front to each of these terms gives me y prime equals c minus cosine x plus x sine x. And if you were to just plug this right in, right, to this equation, you would see that it works for all choices of c, right? It's as simple as that. Works for all choices of c. So that is section 1.1, right? Section 1.1 deals with classification, it deals with checking solutions, and it kind of just introduces the concepts and topics of what a differential equation is. What's an ordinary? What's a partial differential equation, right? What's this first order equation? What's a second order equation? What does it mean for an equation to be linear, right? These kind of things are going to come up again and again for the next few weeks. So it's good that we get this down. Okay, thanks for listening.